In this video, we're going to talk about electron configuration. So where do they come from, how the electrons are arranged. So an electron configuration is simply telling you or giving you an idea of the type of electrons that are present, where you can locate them in a particular atom. Okay, so on a broad basis, if you think about the structure of an atom, you have the nucleus, which is a dense core, okay, and then you have all this area outside the atom where the electrons are located, okay. So now the question is, we have all these electrons, but we need to understand where these electrons are. And why do we need to understand that? Because electrons are the ones that are involved in chemical reactions. So if you don't understand or know where the electrons are, we're not going to be able to make meaningful predictions about a chemical reaction or understand chemical reactions. Okay, so let's kind of take a dive into this. So electrons in general, there are two types of electrons in an atom. Okay, so you have core electrons, and then you have valence electrons. Okay, the core electrons are the electrons that are the inner electrons, and the valence electrons are the electrons that are the outer electrons. Okay, the valence electrons are the electrons that are involved in reactions. While the inner electrons or the core electrons are not involved in reactions. Okay, so let's try. So before we can kind of, now that we've taken a look at a high level picture of what kind of electrons are there, let's take a look at where these electrons reside in the atom. Okay, and the one analogy or one way to think about this is to think about someone's address. So if you're living at a particular location, you have a house number, you have a street name. That street is located in a particular city or a town, and that town is located in a particular zip, right? Okay, so let's kind of dive into that a little bit. So to understand electron configurations, we need to come back to that core, and we need to understand that these electrons are kind of located in these shells, okay, outside the nucleus. You can think of that as being the inner shell, then that's the next, and that's the next. Think of them like layers of an onion that you can peel off, okay. This is a very simple picture of the atom, by the way, okay. There is a quantum mechanical model of the atom, which is a little more complicated, but I don't think we need to understand that to be able to understand electron configurations. So I'm going to present you with a very simple picture and take it from there, okay. So the first shell, so these are called energy levels, okay. So these are called energy levels, and if you just count outwards from the nucleus, that would be 1, that would be 2, that would be 3, okay. So these energy levels are also called quantum numbers, okay. So don't get too worried by the term quantum numbers, okay. It's just a name. So those are quantum numbers, and these quantum numbers, so the certain shells, they're denoted by a quantum number n, okay, small letter n, and the name of this is also called the principal quantum number. So now within each of these n levels, there are sub-levels. So think of them as within the 2, you have certain sub-levels out here. Within the 3, you have certain sub-levels out here, okay. So the sub-levels are given another term, L. That L is called, because it's a sub-level, it's called the subsidiary quantum number, okay. And then there are 2 more quantum numbers which talk about the magnetic orientation of the electron and the spin of the electron. So think of an electron as a small particle. It has a certain magnetic field, and then it also has a certain spin, okay. So the next one is called ML, which is called your, because that's related to the magnetic orientation, it's called the magnetic quantum number. And the last one is ms, that's the spin quantum number, okay? So spin, and I'll just call that qn quantum number, okay? Okay, so those are the 4 quantum numbers that kind of define the address of the electrons in an atom, okay? So now that we understand those quantum numbers, I'm going to erase this. I'm going to show you how the electrons kind of build up in each level. So think of that as the main level, then you have the sub-level, and then you have the sub-sub-levels, okay? So for the main level n, you can have, so n could be any number starting from 1, I'll just write the numbers down here. N could be numbers starting from 1, 2, 3, 4, and so on, okay? So we'll just stop at 4. And then the values of L, okay, which is your subsidiary quantum number that relate to the values of n. So L is given by the ranges 0 to n minus 1. So those are the possible values of L, okay? Again, where does this come from? This comes from quantum mechanics. We don't need to worry about that. We're just going to kind of try to figure out, based on what the value of n is, how many sublevels L can have, okay? So if that's 0 to n minus 1, so if n is equal to 1, then it would be 0, comma, or n minus 1 is 1 minus 1, which is 0, so there's no more. So it's literally L is 0. Now, for when n is equal to 2, you can have 0, and then you can have another level, n minus 1. So that's 2 minus 1 is 1, right? Okay, so I'm going to rewrite this just below this. So here we go. So 2 values of L. For L, n is equal to 3, you can have 0. You could have n minus 1, which is 3 minus 1 is 2. So 0 is the lowest, and then 2 is the highest. But remember, that's a range, 0 to n minus 1, so 0, 1, and 2. And I forgot to mention that this range has only integers, okay? So you're not going to see 1.5 or 1.35 or so on. And the last one is 0, and then n minus 1 is 3, and so the middle ones are going to be 1 and 2, okay? So therefore, for the principal quantum number, if it was 1, you'd have only 1 sublevel, but if it was 3, you'd have 3 sublevels, 1, 2, 3. If it was 4, you'd have 4 sublevels, okay? So it's very interesting. Notice carefully, if you have 1, you have 1 sublevel. If you have 2, you have 2 sublevels, okay? And so then the principal quantum number also dictates the number of sublevels, although the notation for each sublevel is dictated by this little formula out here. Okay, so the next thing is ML. ML tells you the orientation magnetically, and what that means is, from a mathematical standpoint, it basically means how many cells within each sublevel the electrons are distributed in. How far away are they from each other? So you can denote this as a little box. So 0 is basically 1 box, and then 0 and 1, so for 0 it's 1 box, but for 1, now here's the formula for ML. So for each value of L, the formula goes from negative L to positive L. And what that means is, those are all integers, okay? So for 0, it's just 1, because negative 0 to positive 0 is still 0. But for 1 out here, it's going to be negative 1, 0, and positive 1. So that's going to be 3 boxes, and each of those is going to be negative 1, 0, and positive 1, okay? And then the same thing out here. For the first 0, there's only 1 box. For this one, it's going to be 3 boxes. And then for this one, it's going to be 5 boxes, because it's negative 2, negative 1, 0, positive 1, positive 2. Negative 2, negative 1, 0, positive 1, positive 2, okay? And then this one is the same repeat. So the 0 is going to be same as this, the 1 is going to be same as that, the 2 is going to be same as that, but the 3 is going to have how many? -3, -2, -1, 0, +1, +2, +3. So that's 7 boxes. 1, 2, 3, 4, 5, 6, and 7. That's -3, -2, -1, 0, 1, 2, 2, and 3. +1, +2, and +3. Okay, so that's basically how that works. Okay, so now when it comes to MS, that talks about the spin of the electron. So when you start filling up electrons, so here's the rule that you need to remember. So first of all, electrons can have two types of spins, okay? Clockwise or counterclockwise, and they're denoted as a little arrow pointing upwards and a little arrow pointing downwards. So you could have either a spin going up this way or a spin going down this way. I'll switch that and make it downwards this way and then upwards this way. Doesn't matter. Okay, so actually, notationally, this is how it's written: up and then down. Okay, and sometimes they'll draw it with half arrows. Okay, but it means the same thing. So now, if I had to fill up the electrons in these boxes, each box can have a maximum of 2 electrons. So max of 2 electrons in each box. So therefore, if I had to fill up electrons, I'm going to just use a different color out here to fill up the electrons. So for the first one, I can have one going up and one going down. Notice carefully how I used half arrows. Again, doesn't matter. You can use half or you could use full. Okay, I used half simply because it's going to be less cluttered. Out here, now that box is going to look similar to that, so I'm just going to skip that. If you look at this, now here's something interesting. When you fill up electrons in these boxes, you fill them up half first, and then you fill them up full. Okay, so this is dictated by a rule. Okay, and the rule is called Hund's rule of maximum multiplicity. And the rule simply states that when you're trying to fill up these little boxes, by the way, these boxes are called orbitals. Okay, I'll write that down so we don't forget them. So these boxes are orbitals. And what we drew out here, these are called orbital diagrams. So whenever you fill up electrons in boxes, the question is really asking you, what's the orbital diagram? Draw the orbital diagram. And there we have it. Those are orbital diagrams. Okay, coming back to Hund's rule of maximum multiplicity. Hund's rule basically says that when you fill up electrons, you always fill them up unpaired in all the boxes first, and then you pair them up. And the reason for that is because the unpaired electrons are always lower in energy than when you start pairing them up. Okay, so that's the reason. So that's Hund's rule of maximum multiplicity. Now, coming back here, so those two would look similar to this and this. So this one would be, see, unpaired Hund's rule. Again, I'll do them half again, just because these boxes are a little small. So half, 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 and then I'll pair them up. Notice carefully, when I pair them up with the arrows always in the opposite direction. Okay, the electrons are always paired up with opposite spins, not the same direction, opposite spins. Okay, and then you do the same thing out here. But basically, that's what Hund's rule is. Okay, so now that we have Hund's rule of maximum multiplicity, we understand how these pair up. The next step is to kind of figure out, how do you write the electron configuration for an actual element? Okay, so now before we do that, we need to understand, we need a symbol that's going to denote these values of L. Okay, we have numbers out here, but then we have numbers out here, which kind of gets confusing. Okay, so we need a symbol to denote the sublevels. The symbol out here, I'm going to use a different color. So when L is equal to 0, the symbol is a lowercase s. When L is equal to 1, it is a lowercase p. When L is equal to 2, it is a lowercase d, and when L is equal to 3, it is a lowercase f. Okay? Now, so out here, that's a 0, so that's a lowercase s. S 1 corresponds to P. 0, 1, 2, so that's S, P, D, and my S. I should make that a proper lowercase s. There we go. So S, P, D, F. So those are the 4 possibilities. Okay, so now that we understand this, the next thing we need to know is, well, when this S is filled up with electrons, what is it going to be written like? Well, it's going to be written like this. I'll write it out here. Okay, actually, I'll write it out here. 1 for the principal level, S for the sub-level, and the number of electrons is going to be written as a superscript above the S. So 2, number of electrons. Okay, that's all we need to know to write electron configurations. Then there's one more principle we need to know, which is called the build-up principle. And once we know that, we can kind of write electron configurations for any element. So let's take a look at that. Here we have the Aufbau build-up principle. Okay, so that's a German name, Aufbau. I may be pronouncing it incorrectly, so please forgive me. So the way the principle works is you have all these energy levels. So that's the first energy level, that's the second, third, fourth, fifth, sixth, seventh. So these are the principal quantum numbers. 1, 2, 3, 4, 5, 6, 7. Those are the principal quantum numbers. And then you have the sub-levels listed, S, P, D, F, and so on. Okay, and they're listed in terms of energy. Now, the arrows are what you're going to follow to fill up the electrons. Okay, so let's take, for example, we are writing the electronic configuration for carbon. So you look at the periodic table and you find carbon in a box and you find the atomic number for carbon is 6. Okay, 6 means it has 6 protons and 6 electrons. The question for us to decide is, how are those 6 electrons distributed around the nucleus? So for that, you start with the first arrow and you just go downwards, just follow the arrow. Okay, so the electron configuration for carbon is going to be 1s, and we know that s can have a maximum of 2. Then once you finish the first arrow, you start with the second arrow, 2s, maximum of 2, and then second arrow done, third arrow, 2p, we have 6 to work with. We've finished, we've exhausted 2, and p can actually have a maximum of 6 electrons. Why? Because p actually has 3 boxes, if you recall. 3 boxes, and each of them can have 2, so that's a total of 6. So p can have a total of 6. I'll just write it out here. P can have 6, D can have a total of 10, and F can have a total of 14. If you just fill up the boxes, you'll figure out how those numbers come around. Okay, so coming back to carbon, so we've exhausted 4 of the 6 electrons, so we're left with 2 more, so it's going to be 2p2. And there you have it. That's the electron configuration for carbon. Now, let's take a look at another example. Let's say we're doing sodium. You look at the periodic table. Sodium has an atomic number of 11, which means it has 11 electrons as well. So that's going to be 1s2, 2s2, 2p6. 1s2, 2s2, 2p6, and that gives us a total of 10. We have 1 more to go, so we go to 3s1. Okay, so let's do one more. So let's say we have to calculate the electronic configuration for bromine. You look at the periodic table, you find bromine is actually 35. Okay, so that's a big number. So 1s2, 2s2, 2p6, 3s2. Let's keep going. We're going to be going for a while. 3p6, 4s2, 3d10, 4p6, 5s2. Now, let's stop for a minute and count how many electrons we used up, because we cannot go beyond 35. So 4 and 6 is 10. 2 and 6 is 18, so that's 10 and 18 is, 2 and 6 is 8, plus 10 is 18, plus another 10, so that's what, 28, plus 2, 30, 36, and 2, 38. So we went over 35, so we don't need the 5s2, and out here we need, it's just a 4p5. So that gives us a total of 35, okay? So there you have it. That's how you write the electron configurations for elements using this our buildup principle. Now, the next question that we have to kind of decide is, if you recall, when we started this video, we talked about how do you, that there are two types of electrons, core electrons and valence electrons, okay? And the core electrons are not involved in chemical bonding, and valence electrons are the ones involved in chemical bonding or chemical reactions. So it's important for us to understand which of these electrons, now that we have the distribution or the electron configuration, which of these are going to be involved in bonding and which of these are not involved in bonding. So to figure that out, we have to kind of understand where these elements are in the periodic table, okay? So if we take carbon, for example, and you kind of take a look at the periodic table, I encourage you to pause the video, grab a periodic table and take a look at it. You will see that, and I'm going to go ahead and erase this since we don't need this, so maybe I'll just draw out a small miniature version of the periodic table out here so we can kind of look at it together. So the periodic table kind of has one box out here, and then it has two rows out here, two columns out here, and then it has another one out here. Then you have a big block in between. We don't care about that right now. And then you have you actually have 1, 2, 3, 4, 5, and then you have a sixth one out here. So these are the noble gases. Okay, so now let's fill that up. Okay, so we can draw that there. Okay, so out here you have hydrogen, out here you have helium, and then below hydrogen you have lithium, and then if you go from left to right you have beryllium, which is Be, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, so we have enough to be able to figure out what's happening. So what we have out here are the noble gases. Noble gases is just one way to say that the electron configuration is full, okay, which means it's maxed out, okay. So, and one thing to keep in mind is every element wants to be a noble gas, so wants to become a noble gas, okay. So to figure out how many valence electrons it has, you just have to count up to the next noble gas, okay. So in the case of carbon, we have 6 electrons. So now notice carefully what happened. The 1s2 is actually, if I count the periods of the periodic table, 1, 2, 3, 4, and then you have 5, and you have 6, and then that's the 7th period, okay. I did not draw the lanthanides and actinides out here. Don't worry about that for now. But see, that 1s2 is 1s1 is hydrogen, 1s2 is helium. I'll kind of draw it out and show you. That's 1s1, that's 1s2, okay? And then as you wrap around from left to right, that has 3, atomic number 3. So now you're starting the second level. So that's 2s. Let's use a different color out here, so it's a little more clear. Let's use purple. So that's going to be 2s1. So that's 2s1. So lithium is going to be 1s2, 2s1, okay? And beryllium is going to be 2s2. Boron is going to be 2. Now see, 2s is over because s can have a maximum of 2. Now we're going to the 2p's. So that's the p's, 2p1 and 2p2. And that's exactly what we predicted for carbon using the Aufbau buildup principle. So at this point in time, remember, P can have a maximum of 6, okay? So nitrogen should be 2p3, 2p4, 2p5, and then neon is 2p6, okay? So that means you have to count up to the nearest noble gas. 1, 2, 3, 4. So if carbon had 4 more electrons, it would be neon, okay? It would have the same electron configuration as neon. Now, so then the question arises, which ones are the valence electrons? So the valence electrons are simply the number of electrons in excess of the previous noble gas. So that's the previous noble gas, helium. How many electrons does carbon have in excess of the previous noble gas? 1, 2, 3, 4. 4 valence electrons. Let's call that VE. 4 valence electrons. Let's take a look at sodium. Same logic. So it turns out sodium is actually sitting right here, okay? And sodium has 11. So sodium has got a 3s1 out here, okay? So what you have out here is you have 2s filled up, 2p is going up to 2p6, and then then it's a 3s1, see? So now sodium has the noble gas before sodium is neon, so sodium has 1 more electron than the previous noble gas. So it turns out sodium has 1 valence electron, okay? And turns out, now if you can kind of go down this list, we're going to try to track our way down to bromine. So below fluorine, you have chlorine, and then you have bromine sitting out here, okay? So below neon, you have argon. So in order to find the number of electrons bromine has, valence electrons bromine has, you just need to go backwards this way, and you'll see going backwards, so that's 5, right? 1, 2, 3, 4, 5, and then those are actually 10, okay? So everything in this block, there are actually 10 columns, okay? So that's 10 plus 5, 15, okay? And then 2 more, okay, before you can hit argon. So that's 17. So bromine actually has 17 valence electrons. Now it turns out, for the most part, for the most of the chemical bonding that takes place, usually these electrons, they don't really get involved in bonding unless the bonding is a special type of bonding, okay? So for the most part, bromine can be thought of the 17 minus the 10, okay? So anything that sits on this side and has these 10 out here, for the most part, you can ignore these 10 out here, and then, so turns out, you can also say that bromine has 7 valence electrons, and that would be correct as well, okay? So now that's basically how you kind of figure out. So now that we know the valence electrons, we have enough information to be able to understand the bonding that these elements will undergo. So since we talked about bonding so much, let's talk about how this bonding takes place. So for bonding to occur, an atom actually has to either lose electrons or gain electrons, okay? So when electrons are lost, I'll just write it out here. When atoms lose electrons, then they become something called cations. When they gain electrons, then they become anions. And then the question is, how many electrons does a cation lose, or how many it's going to gain, is going to be dictated by the number of valence electrons it has, okay? So now, remember, every element will always try to get the same electronic configuration as the closest noble gas, okay? And that closest noble gas may be sitting right next to it, or it might be sitting, if it's sodium, for example, the closest noble gas to sodium is going to be neon, okay? So in order to get there, it's going to try to choose the easiest way to get there, okay? So if an element is sitting in this group, it's going to be easier. So let's take sodium. Let's focus our attention on sodium. I'm just going to circle it out here. If we're looking at sodium, it's going to be easier for sodium to lose 1 electron. That way it can have the same electron configuration as neon. as opposed to gaining 7 electrons. 1, 2, 3, 4, 5, 6, 7. It's going to gain 7 electrons to become argon. So it's easier to lose electrons, okay? So therefore sodium, if you're looking at an atom of sodium, it's going to lose electrons. So sodium will lose an electron to form an ion, a cation in this case, because it lost 1 electron and that electron is popped off this way. So you can denote it that way. And notice carefully, if you lose 1 electron, then now you have 1 less electron than the number of protons in the nucleus. Therefore, you have 1 excess positive charge. Therefore, you write the sodium ion with a positive charge, because that's the residual positive charge after the protons and electrons cancel out whatever they can with each other. Now, if you take, for example, what's sitting on the right of sodium, so that's actually magnesium is sitting out here. Magnesium has 12, so magnesium is going to lose 2 electrons to become neon. So magnesium is going to be written as magnesium 2 plus, because so for each electron it loses, there's 1 excess proton. Therefore, you just add up the charges, plus 2 electrons. Okay, so basically anything sitting out here, I'm going to write that in red out here. It's going to be easier for it to lose 1 electron. So that's going to be plus 1. It's going to be easier for this to lose 2 electrons, plus 2, or 2 plus. It's going to be easier to lose 3 electrons, plus 3. When you're out here, you're kind of midway. So you can either gain or lose 4. So we're going to write plus 4, minus 4, but that usually doesn't happen, okay? Some other stuff happens that we won't get into right now. When you're out here, when you're at nitrogen, for example, let's take a look at what happens with nitrogen. For nitrogen, it's easier for nitrogen to gain 3 electrons to become neon as opposed to losing 5 electrons to become helium. See? 1, 2, 3, 4, 5. It has to lose 5 to become helium. So therefore, it'll gain 3 electrons, and so therefore nitrogen is going to take up 3 electrons. So now you actually have 3 fewer protons in the nucleus and 3 excess electrons outside. So it's going to be an N3 minus, okay? So that's going to be an anion, okay? So anything sitting out here is going to have a negative 3 charge. Anything sitting out here is going to gain 2 electrons. So that's negative 2. And then anything sitting out here is going to gain 1 electron, so that's negative 1.